For example, we have seen that zinc can displace copper from its solution. This reaction we have seen because zinc has more tendency to get oxidized, right? That means zinc has more oxidation potential than copper, but we are not concerned about oxidation potential, we are concerned about reduction potential. Zinc has less reduction potential than copper. Correct? Hope you understand what I'm trying to say. See, zinc has more oxidation. Zinc 2Zn2 plus, this reaction is more favorable, right? That means zinc has more oxidation potential than copper. But we have the chart for reduction potential. That means zinc has less reduction potential than copper. That means the one which has less reduction potential will displace the one with higher reduction potential, right? I can say that less reduction potential metal will displace higher reduction potential metal. That means let's put this in arranged order. So we have magnesium. So let's see where is magnesium. Aluminium we have, right? So let's see where is aluminium first. Aluminium is this guy. Then we have copper. So we have copper in this position. Then we have iron. Iron is this position. And then we have Mg. This position. And then we have zinc. In this position. Correct? I told the lower one will displace the higher one. That is, this guy can displace all of these guys, right? So the order will be Mg is the first, then we have aluminium, then we have zinc, and then we have iron, and then we have copper. And we have seen that zinc can displace copper. That means this series is correct. Correct? Magnesium, aluminium, zinc, iron, copper. Correct? Hope you understand. See, in this case I have seen that zinc 2Zn2 plus, right? Or you can just see this reaction. Mg2 plus to Mg has lesser value. Cu plus to Cu has more value. That means this reaction is more favorable. More favorable reaction, right? As compared to these reactions. These are less favorable reactions. So in this reaction, if you see, copper is getting displaced from its salt. That means copper can easily be displaced from its salt. Here, magnesium is getting displaced from its salt, but this is less favorable reaction. That means it is difficult to replace magnesium from its salt. Right? So magnesium is the one which will replace other from their salt. Let's take another numerical. It has been given that standard electrode potential, that is nothing but standard reduction potential. See, K plus 2K reduction, Ag plus 2Ag reduction, Hg2 plus 2Hg reduction, Mg plus 2Mg reduction, and Cr3 plus 2Cr3 reduction. We have to arrange these metals in increasing order of their reducing power. Right? See, reducing power is what? Reducing power is ability to reduce other. That means ability to get oxidized correct? See, the one which will get oxidized on its own will reduce others, right? So ability to get oxidized. So this is the reduction potential, right? So higher reduction potential implies ease to get reduced, right? That means lower reduction potential will imply what? Ease to get oxidized. See, higher reduction potential means it has positive value, that means this reaction is feasible. That means it can, for example, Cu2 plus to Cu, the value is 0.34 volt, right? That means this reaction is pretty easy, feasible as compared to H plus to H. This is 0 volt, right? This reaction is more feasible. Reaction 1 is more feasible than reaction 2. So higher reduction potential means the reaction, it is easy to get reduced, correct? Lower reduction potential means it is easy to get oxidized. We are looking for ability to get oxidized. That means I am looking for lower reduction potential. That means the one which has least reduction potential will be oxidized first. So which has the least reduction potential? So let's see the values here. Let's put the values in ascending order, right? Let's put first K plus to K, it is minus 2.93 volt. Ag plus to Ag is plus 0.8 volt. Hg plus 2 to Hg plus 0.79 volt. And then Mg 2 plus to Mg minus 2.37 volt. And then I have Cr3 plus to Cr, I have minus 0.74 volt. So which is the least value here? The least value is this guy, right? Minus 2.93. You see, this is the least. What is the second value? Second least is this guy. What is the third value? Third is this negative value, and all positive left. So fourth will be minus plus 0.79 and then only plus 0.80. This is the order. This is the order. This K will have highest reducing power, and then this, then chromium, then Hg, mercury, and then silver. This is the order. So the question says depict the galvanic reaction when this reaction take place. Zinc is oxidized to zinc 2 plus, and silver plus is reduced to silver. Which electrode is negative charge, the carrier of current in the cell, and individual reaction at each electrode. So we have seen the as per convention, this is anode and this is cathode, correct? By IUPAC convention. Anode is oxidation, which is getting oxidized? Zinc, that is zinc. So it will be a zinc sulfate solution. And reduced is Ag plus, this is Ag sulfur, that solution itself, right? Or it is Ag plus 2, let's keep like this, and this is Ag plus 2. Right, this is general plus 2 electrolytes, and this is Ag plus 2 electrolyte, and this will be Ag, silver. I mean, this color doesn't look like silver, but since we didn't know which one is zinc, which one is silver, we just took this picture. Now what will happen? Zinc will become Zn plus 2, you'll have more electrons here. So electrons will flow from here to here. Since the electron is flowing from here to here, this gets negative charge, this gets positive. Please note, you can't just say blindly anode is negative, cathode is positive. That you have to find from the reaction, right? Zinc is losing electrons. So if you see, the reaction at anode is what? zinc is losing electron to give 2 electrons. This is a reaction at anode, and cathode reaction is what? 2Ag plus 2 electron gives Ag silver. This is cathode, right? So since which electrode has negative charge? Obviously this is zinc electrode. The answer is zinc. First part done. Correct. So next question is the carrier of current in the cell. We know that it is electrons that carry the current here outside the cell, but it is the ions. For example, if you see here, right, with zinc sulfate, this is silver sulfate or silver nitrate. The nitrate ion or Ag plus will go from here to here. This is Ag plus, and let's put this zinc sulfate. Sorry, this will be zinc plus that will go, because here we have more zinc plus, and here Ag plus is used. So let's suppose nitrate ion, you have the N3 minus ion. AgNO3 you have, let's suppose. So zinc, this is ions which will move, right, in the cell. So ions are the current carrier in the cell, inside the cell, and the electrons are the current carrier outside the cell. Why? Because the Sol bridge is there, right? So here, because zinc becomes Zn2 plus, the of Zn2 plus here, so zinc Zn2 plus will move from left to right. Ag plus AgNO3, let's suppose I have that broke into Ag plus and NO3 minus. Correct. So this Ag plus is used by this reaction. NO3 minus is there. A lot of NO3 minus will move from right to left. So that is my answer. Third is individual reaction at each electrode. We have given that. At anode we have zinc oxidized to Zn2 plus, and at cathode Ag plus is reduced to Ag.